Look at the window next to you on your next flight. The corners are curved, not slightly rounded, deliberately, geometrically curved. Every window on every commercial aircraft in service today shares this feature. It is not an aesthetic decision. It is the direct consequence of 3 aircraft falling out of the sky in the 1950s, and the investigation that followed. The aircraft was the Havilland Comet. It entered commercial service in 1952 as the world's first jet-powered passenger airliner. It was faster than anything that had come before it, capable of cruising at altitudes above 12,000 meters where the air was thin and smooth, and the ride was unlike anything piston engine travel had offered. Passengers and airlines responded immediately. The Comet was the future of commercial aviation. It was also killing people. In January 1954, BOAC Flight 781 broke apart over the Mediterranean, near the island of Elba. 35 people died. 3 months later, South African Airways Flight 201 disintegrated over the same sea, under almost identical circumstances. In total, 3 comets were lost in rapid succession, with no survivors and no obvious explanation. The aircraft had not been struck by weather, had not reported any emergency, and had not shown any sign of distress before the structural failures. They simply came apart at altitude. The British government launched one of the most thorough accident investigations in aviation history up to that point. The Royal Navy recovered wreckage from the Mediterranean seabed. Engineers at the Royal Aircraft Establishment in Farnborough subjected a Comet fuselage to repeated pressurization cycles in a water tank, filling and draining it thousands of times to simulate the stress of repeated flights. What they found changed the fundamental rules of aircraft design. The Comet's windows were square, with sharp corners. This was a functional choice. Square windows allowed more light into the cabin and gave passengers a wider view. But under the conditions of pressurized high-altitude flight, those corners were behaving in a way the designers had not fully accounted for. Every time a pressurized aircraft climbs to altitude, the pressure differential between the cabin interior and the outside atmosphere causes the fuselage to expand slightly. The cabin is pressurized to roughly 0.75 atmospheres, while the exterior at cruising altitude may be as low as 0.25 atmospheres. That difference, half an atmosphere across the entire skin of the aircraft, loads the fuselage structure with significant tensile stress on every flight. When the aircraft descends and the pressure equalizes, the fuselage relaxes. Each flight is one complete stress cycle. Over thousands of flights, this cycling accumulates damage in the metal, a process called metal fatigue. Metal fatigue is not the same as a single overload. A metal component can survive a force far beyond its design limit, if applied once. But the same component, subjected to a stress well within its design limit, repeated hundreds of thousands of times, will eventually crack. The cracks start small, often microscopic, and propagate incrementally with each cycle, until the remaining cross-section of material can no longer carry the load. At that point, the failure is sudden and total. The Comet investigation identified the corners of the square windows as the initiation points for fatigue cracking. The reason is a phenomenon called stress concentration. When a flat plate with a hole is placed under tension, the stress does not distribute evenly around the perimeter of the hole. At points where the hole boundary curves sharply, particularly at corners, the local stress is significantly higher than the average stress in the surrounding material. The sharper the corner, the greater the stress concentration at that point. The relationship is described by a stress concentration factor, a multiplier that tells engineers how much higher the local stress is at a geometric discontinuity compared to the nominal stress in the part. For a circular hole in a flat plate under uniaxial tension, the stress concentration factor at the edge of the hole is approximately 3. For a square hole with sharp corners, the stress concentration factor at each corner is substantially higher. The exact value depends on the corner radius. But for a truly sharp corner, It approaches values that make fatigue cracking under cyclic loading essentially inevitable over a sufficient number of cycles. The Comet's designers were not ignorant of stress concentration. The concept was understood. But the combination of factors that made the Comet's window corners so dangerous, the high cabin pressure differential at the altitudes the jet could reach, the number of pressurization cycles accumulated over a relatively short service life, and the specific geometry of the window cutouts, had not been fully stress-tested under realistic conditions before the aircraft entered service. The Farnborough pressurization tests, which might have revealed the problem, were conducted after the crashes, rather than before. The fix was immediate and became universal. Round the corners, a circular or elliptical window opening distributes the stress around its perimeter without creating high concentration points. The stress concentration factor for a circular hole is 3, the same at every point around the circumference, with no spikes. By eliminating the corners, engineers eliminated the initiation sites for fatigue cracking under pressurization cycling. Every commercial aircraft designed after the Comet investigations incorporated rounded window corners as a basic structural requirement. The geometry involved is simple enough to state in a sentence, but its implications extend far beyond windows. The Comet investigation established the principle that cyclic fatigue under pressurization loading was a critical design consideration for all pressurized aircraft, not just at windows, but at every cutout, every joint, every structural discontinuity in the fuselage. Doors, cargo hatches, emergency exit cutouts, and antenna fairings all required the same attention to corner geometry and stress concentration. The investigation also established the value of full-scale fatigue testing before certification, the practice of subjecting a complete airframe to thousands of simulated pressurization cycles on the ground before the aircraft enters service. Modern aircraft certification requires exactly this. A new aircraft type must demonstrate through physical testing that its structure can withstand a defined number of pressurization cycles, typically representing twice the expected service life of the aircraft, without developing fatigue cracks that compromise structural integrity. The test articles used for this certification are full production airframes, not scale models, instrumented with strain gauges and subjected to repeated pressure cycles in purpose-built test facilities. For a large commercial aircraft with a design service life of 90,000 flight cycles, this means the certification test article must survive 180,000 simulated cycles without failure. The Boeing 737, which has been in production in various forms since 1968, has accumulated more operational flight cycles than any other commercial aircraft type in history. Individual 737 airframes, used on high-frequency short-haul routes, may accumulate 3,000 or more pressurization cycles per year, far more than a long-haul wide-body that makes fewer but longer flights. High-cycle aircraft receive more frequent and more detailed structural inspections, with particular attention to window frames, door surrounds, and any location where a structural cutout creates a potential stress concentration point. The Airbus A380 introduced an additional layer of complexity in this area. Its upper deck extends the full length of the fuselage, creating a double bubble cross-section rather than the single circular or oval section used on conventional aircraft. The stress distribution around window cutouts in a double bubble fuselage differs from that in a conventional section, requiring specific analysis and testing to verify that the rounded corner geometry provides adequate protection against fatigue initiation at the actual stress levels present in that specific structure. Composite materials, which now make up a significant portion of the structure on aircraft like the Boeing 787 and Airbus A350, change the fatigue equation in important ways. Carbon fiber reinforced polymer does not exhibit metal fatigue in the same way that aluminum does. Its failure mode under cyclic loading is different: delamination and fiber fracture rather than crack propagation, and its resistance to cyclic stress is generally higher than aluminum. for the same structural weight. This means that composite fuselage sections can be designed with somewhat less conservative approaches to stress concentration at cutouts, though rounded corners remain standard practice because the underlying structural logic still applies. The window you look through on a commercial flight is smaller than it could be, and curved where it could be straight because of a sequence of events that began over the Mediterranean in 1954. The engineers who designed the Comet were building the most advanced commercial aircraft in the world with the tools and knowledge available to them. The gaps in that knowledge became visible only after the aircraft entered service, in the worst possible way. The response to those gaps, systematic fatigue testing, mandatory rounded corners, stress concentration analysis as a standard design tool, defines how every pressurized aircraft has been built since. A sharp corner on an aircraft window is not a minor detail. Under the conditions of pressurized high-altitude flight, repeated thousands of times over a service life measured in decades, it is a crack waiting to start. The absence of that corner on every window you have ever looked through on a commercial flight is the reason the aircraft arrived. There is one further dimension to this story that is worth understanding. The Comet investigation did not just change window geometry. It changed the relationship between aviation regulators and aircraft manufacturers on the question of certification evidence. Before the Comet crashes, certification of a new aircraft type relied heavily on analysis and component testing. Engineers calculated the expected stresses, tested individual components to verify those calculations, and certified the aircraft on the basis that the analysis was sound. Full-scale fatigue testing of a complete airframe was not a standard requirement. The Comet had been certified under this approach, and the certification was technically valid given the state of knowledge at the time. After the investigation, it became clear that analysis alone was insufficient for pressurized aircraft structures. The interactions between components, the effects of manufacturing variability, and the cumulative behavior of a complete structure under thousands of cycles could not be fully captured by calculations on individual parts. Only a physical test of the complete structure, under realistic loading conditions, could provide the evidence regulators needed to be confident the aircraft would survive its intended service life. This shift from analysis-based to test-based certification for fatigue-critical structures was one of the most consequential regulatory changes in commercial aviation history. It added significant cost and time to the development of new aircraft types. It also prevented failures that would otherwise have occurred. The 1988 Aloha Airlines incident, in which a Boeing 737 lost a large section of its upper fuselage at altitude, demonstrated that even with improved design standards, high cycle operation could produce fatigue damage beyond what certification testing had revealed. That incident further refined inspection requirements for high cycle airframes and reinforced the principle that structural certification is not a one-time event, but an ongoing obligation across the aircraft's service life. The window frame you rest your head against on a long flight has been shaped by 70 years of accumulated accident investigation, regulatory response, and engineering refinement. Its rounded corners carry the history of every aircraft that came before it, and the lessons extracted from the ones that did not survive.